Now that we've made citrate, or it's like citric acid, we now have to turn it into isocitrate, so it's in the correct orientation. So now we're going from citrate to isocitrate. If I scroll down here, it's this complicated mess here. Now this is just a iron sulfur cluster here. Um, it's just a protein. What's important here is this iron right here is going to be binding using basically intermolecular forces to stabilize citrate. So let me show you how this goes. Okay, so I already have it drawn out. This right here is just citrate, okay? We made it in the previous step, okay? C bonded to CH2, COO minus, C bonded to CH2, CO minus, and then coming off this central carbon is another carboxylate and an alcohol, okay? So here's my iron group, and I just simplified it here. I have X's coming off, meaning other things. It doesn't actually really matter, okay? This iron sort of sulfate cofactor. And here I even simplified it more and just put iron, okay, because that's the main part of that whole structure there. So what this iron is doing initially is sort of binding through intermolecular forces here with the oxygen and hydrogen. And what this does is stabilize this here so it can react, okay? So let's see what's going on initially. Now the first thing that comes in is a base. A base is going to be any of your amino acids like lysine or something can act as a base. And it's going to take off a hydrogen right here. Now I don't have it explicitly shown, but it's going to take it off. And then it's going to leave its electrons right here. And you see right here, instead of having CH2, I now have a CH. And right here between these two carbons, I now have a double bond, okay? The other thing that's going to happen is this carbon already has 4 bonds, so something has to leave. The best leaving group is going to be this OH, and it's going to grab an acidic hydrogen as it leaves, so that OH will leave as H2O, which is water. Okay, so it's no longer on here. So that's what happens initially. Again, this iron is stabilizing everything. It's really stabilizing the transitional step, but basically it's making it so this will react, okay? So now I have this double bond here, and my OH is gone and left as water, okay? Now what happens? Now this iron here is still there, stabilizing everything. Now this water basically is going to be attacked by this double bond, okay? It's going to bind right there, and that going to have too many hydrogens on it. So hydrogen then, because let me show you the intermediate there, so you kind of remember COH, COO minus, and there'll be a plus charge right here. And then let's see, yeah, CH2COO minus. So there's a plus charge here. So there's an extra hydrogen. Here's our water on there, and what happens is this basically this hydrogen is going to move over here to stabilize that, okay, to put a bond there. Okay, so when we do that, you have this final structure right here. Okay, so basically you lose water, then water comes back in. It's all stabilized by this iron group here. And so let's see what we just did, okay? So what we did is off this carbon right here, this was your central carbon, which is this carbon right here. Now, instead of having an OH group, it just has a hydrogen coming off. And this carbon right here, which is this one here, I'm going to box around it. Instead of having 2 hydrogens, we now have a hydrogen and an OH. So basically, this OH, let me change my color here. This OH, through this mechanism, basically moved over to the CH2, is what happened. This long, drawn-out process is basically to move the OH to a different carbon. And this is our isocitrate. And now this will start the beginning of getting ATP and NADH.